So right now, like as you listen to this, you are actually inhaling thousands of fungal spores and bacteria.
Yeah, and a whole lot of viruses too.
Right. And by the time this deep dive ends, your body will have just silently fought off multiple microscopic threats that, frankly, would have killed a Victorian king.
Oh, absolutely. Wouldn't have stood a
I
chance.
mean, you touch a doorknob, you breathe the air on a crowded subway, and you are just constantly being bombarded. But you don't even notice it, because you have this invisible microscopic shield quietly doing its job.
It is remarkably efficient. The baseline state of human existence is actually a state of constant low-grade biological warfare.
That sounds exhausting, honestly.
It kind of is, but we only ever really notice our immune system when we get the sniffles and it has to work a little overtime, creating inflammation to clear something out.
Right, but for this deep dive, we're asking a much bigger, much heavier question for you to consider. What happens when that shield doesn't just crack but fundamentally fails? Like when the system completely forgets how to work?
Yeah, that's the real question.
Because today, we're diving into the fascinating pathophysiology of immunodeficiency. And the mission here is to figure out exactly how these defenses break down, bust some pretty massive misconceptions. Spoiler alert, it is not always about having a low white blood cell count, and really understand how weakened immunity dictates disease.
Yeah, and to really ground this conversation, we have to look past the textbook shorthand. Usually, you'll hear immunodeficiency described simply as a weakened immune system.
Which sounds so simple.
Right, but that framing actually hides the actual biology. Immunodeficiency isn't just one single disease.
Okay.
It's this broad category encompassing dozens of entirely distinct mechanical failures. They all just happen to converge on one single dangerous downstream problem.
Which is,
The body loses its ability to clear pathogens that it would normally just vaporize without a second thought.
wow. So to truly understand what a broken shield looks like, I feel like we have to go back to the first time someone actually spotted the exact missing piece of the armor, because before a certain point in medical history, people just got sick and nobody really knew why.
Exactly. And the birth of clinical immunology as a discipline actually traces back to one specific case report in 1952.
Oh, wow, that recent.
Yeah, there was an Army pediatrician named Ogden Bruton working at Walter Reed Hospital. And he had this 8-year-old patient who was just unimaginably sick.
Like, how sick are we talking?
Well, over a 4-year period, this young boy had suffered 14 episodes of severe bacterial infection.
14.
Yeah, including sepsis and pneumonia. And it was always from the exact same class of bacteria, primarily Streptococcus pneumonia.
I mean, 14 episodes of sepsis and pneumonia by age 8, that is just devastating for a child to endure.
It really is. And Bruton realized, this couldn't just be bad luck. So he did something incredibly innovative for the time. He used a relatively new technique called serum protein electrophoresis to look at the boy's blood.
Electrophoresis.
Yeah.
That's where they use electricity, right?
Exactly. Basically, you run an electrical current through the blood serum, and that forces the different proteins to separate based on their size and their charge.
Okay.
And when Bruton looked at the results, he found this gaping hole. The boy had absolutely zero circulating gamma globulin.
Wait, meaning he had no antibodies?
None.
Or none at all?
None at all. Bruton actually named the condition agammaglobulinemia. And he started giving the boy regular injections of pooled donor gamma globulin to just, manually replace what was missing.
And did it work?
It did. The infection stopped. When he published this case, it was the very first time a specific molecular defect had been directly linked to a specific pattern of disease.
That's incredible.
Yeah, and we now know this is caused by a mutation in a specific gene called BTK. That gene acts like an instruction manual for building a signal switch in B cells. Without the switch, the cells just never mature to produce antibodies.
Now, let me push back on this premise a little bit on behalf of anyone listening who has kids, because children are basically walking petri dishes.
They really are.
Right, they get sick all the time. How did Bruton know this boy wasn't just having a terrible run of daycare bugs? Like, if I get, 5 bad colds this winter, does that mean I'm immunodeficient?
I love that you asked that because that is the most common misconception clinicians have to navigate. Immunodeficiency is not just catching frequent colds.
Okay, good to know.
Right. The immune system is supposed to react to new pathogens. Clinicians don't look for the sheer frequency of common sniffles. They look for a very specific pattern of failure. They use a mnemonic called the SPUR criteria to separate, normal childhood illness from a true defect.
SPR, like cowboy boots.
Exactly.
Okay, let's break those down.
So the S stands for severe. We're talking infections that require IV antibiotics or hospitalization, not just, bed rest and soup.
Got it.
The P is for persistent. These are infections that simply won't clear up even with standard treatment.
Okay.
The U is for unusual. This means getting sick from rare, weak bugs that normally just don't harm humans at all, or finding infections in weird, rare sites of the body like a liver abscess.
Oh, wow. Yeah, that would be unusual.
Right. And finally, the R is for recurrent. So 14 bouts of life-threatening pneumonia and sepsis fits the severe and recurrent criteria perfectly. Getting a runny nose from your toddler every month, that's just biology doing its job.
Okay, that makes a lot of sense. So Bruton found a missing antibody, but antibodies are just one weapon in the arsenal. How do doctors today know which part of the system is broken when a patient walks in? Because looking at the sources, the immune system is just incredibly complex.
It is.
So let's build an analogy here from first principles to help visualize it. I was thinking we could compare it to different branches of a security force.
Oh, I like that. That works perfectly. Let's start with the front lines.
Right. So first you have your innate immunity, things like phagocytes and physical barriers like your skin.
Yeah.
These are basically the bouncers at the door. They are fast, they are aggressive, but they're totally nonspecific. They just see a pathogen doesn't have a VIP wristband and they tackle it.
And importantly, those bouncers have no memory. They treat a bug the exact same way on the 50th encounter as they did on the very first. But if the pathogen gets past the bouncers, you need the next branch, which is humoral immunity.
Right, which is your B cells and the antibodies they produce. So in our security analogy, this is like aerial support.
Yes, exactly.
They drop neutralizing payloads, the antibodies,
Yeah.
on targets outside the buildings. They take out toxins and bacteria floating freely in the bloodstream before they can breach a cell.
But some pathogens, especially viruses, they're stealthy. They slip inside the buildings, meaning your body cells, and they just hide.
So aerial support can't see them anymore.
Right. That's when you need cell-mediated immunity, the T cells.
The tactical SWAT team.
Yes.
They actually go hand to hand inside the buildings. They clear out rooms, fighting viruses, fungi, and any pathogens that have breached the perimeter and set up camp inside your own cells.
Exactly. And connecting this to the bigger picture of clinical diagnosis, this three-part architecture is really the most important first principle of immunology. A defect in any one of those specific arms creates a highly specific infection signature.
Oh, okay.
Clinicians essentially reverse engineer which arm is broken based entirely on what kind of infections the patient keeps getting.
Meaning the type of bug that gets in literally tells you which guard was off duty.
Precisely. If your humoral immunity, your aerial support is broken, you're going to see recurrent bacterial infections in the bloodstream or respiratory tract because those bacteria just aren't being tagged and neutralized.
Makes sense.
But if your T cells of the SWAT team are defective, you're going to get overwhelmed by viruses and fungi because nothing is clearing out the cells that are already infected.
Okay, let's unpack this. Because if the immune system is a security force, you might think finding a defect is as simple as just counting the soldiers. Like, you draw some blood, count the white blood cells, and if the number is normal, you're fine.
You'd think so, yeah.
But the sources show that is a massive and incredibly dangerous trap.
It is. It's what we call the illusion of numbers. And the clearest example of this is a condition called chronic granulomatous disease, or CGD.
Okay, CGD.
Right. So if a patient with CGD comes into the clinic and you do a standard blood draw, their white blood cell count looks completely normal. They have plenty of phagocytes.
So the bouncers are all standing at the door.
Wearing the shirts, looking tough, ready to work.
Right.
And they actually do the first part of their job perfectly. They see an invading bacteria, they grab it, and they swallow it.
Okay, so what's the problem?
Here is the critical mechanical failure. Due to a defective enzyme called NADPH oxidase, those bouncers cannot generate what's called a respiratory burst.
Wait, so they can swallow the bug, but they can't deploy the toxic chemicals, like the hydrogen peroxide and bleach-like compounds, to actually digest and kill it.
Exactly. The bacteria just sits there, perfectly alive, inside the immune cell that was supposed to destroy it.
That is terrifying.
It is. And the body realizes it can't kill the pathogen, so it initiates this fascinating fallback protocol. It builds a physical wall around the infected cell to quarantine it.
Like it's entombing it.
Yes. And these walled-off clusters of immune cells and live pathogens are called granulomas. Over time, they cause immense structural damage, blocking the gut, the liver, or the urinary tract.
Wow.
These patients get very specific, severe infections from bugs like Staph aureus, which have their own defenses that make them especially hard to kill without that respiratory burst.
This is just mind-bending. Immunodeficiency isn't just about not having the cells, it's a functional failure. You can have a massive army, but if their weapons jam, you are still completely defenseless.
Perfectly said.
And that functional nuance is exactly why you need specialized tests, right? Like the DHR flow cytometry test that was mentioned in the literature.
Yeah, that test is a perfect example of looking at function over numbers.
Yeah.
In a DHR test, clinicians take the patient's white blood cells and expose them to a fluorescent dye.
Okay.
If the cell can successfully generate that toxic respiratory burst, the chemical reaction actually makes the dye glow bright under a laser.
Oh, that's cool.
Right, but if the cell is defective, like in CGD, it just stays dark. You are literally watching to see if the weapons fire.
That realization that it's about function and intricate cellular machinery, not just quantity, it actually shattered the medical dictionary recently. Up until 2022, the medical community called all of these genetic defects primary immunodeficiencies. But then the International Union of Immunological Societies completely rebranded the category to inborn errors of immunity, or IEI. Why go through the trouble of a massive rebrand?
Because genetic sequencing evolves so dramatically. As immunologists sequenced more genomes, they found something just baffling. They found patients who had the exact same broken genes as immunodeficient patients, but they weren't getting unusual infections.
Wait, then what was happening to them?
Instead, they had severe autoimmunity. Their immune systems were aggressively attacking their own healthy tissues, or they had severe allergies or chronic inflammation.
It's like the wiring in a car. It's not just that the brakes are missing, which would be your classic deficiency. Sometimes the wiring is so crossed that hitting the brakes actually activates the accelerator, which is the autoimmunity.
That's a great way to look at it.
They aren't opposites at all. They're two sides of the exact same dysregulation coin.
And that car analogy highlights exactly why the term deficiency was no longer accurate. The underlying hardware failure is the same. There are conditions with complex names like IPEX syndrome or ALPS, but the simple way to understand them is that they remove a regulatory brake on the immune system. When those regulatory T cells fail, you can simultaneously be unable to fight off a simple fungal infection while your immune system aggressively destroys your own thyroid or pancreas.
God, the system isn't just weak. It's confused.
Highly confused.
It's a terrifying paradox to consider. But what happens when the most critical parts of the system, both the SWAT team and the aerial support, are completely missing from the very moment of birth?
That brings us to the most severe end of the spectrum, which is severe combined immunodeficiency, or SCID.
SCID?
Yeah. This is a condition where a genetic defect fundamentally cripples both the T cells and the B cells. It is the absolute worst possible combination, leaving a newborn entirely without an adaptive immune system. It occurs in roughly 1 in 58,000 births.
This is the famous boy in the bubble story that captured the public's attention in the 70s, right?
Yes, David Vetter. He was born in Texas in 1971 with SCID. Because even a common cold virus could be instantly fatal without T or B cells, he was placed inside a sterile plastic isolation chamber within seconds of being born.
Just seconds.
Yeah, and he lived almost his entire 12-year life inside that bubble, waiting for science to catch up and find a cure.
And the tragedy of his story is just profound. In 1983, he finally received a bone marrow transplant from his sister. It was the best genetic match available, and the hope was that her healthy bone marrow stem cells would grow into a new immune system for him.
That was the goal, yes.
But the donor marrow contained a latent, dormant Epstein-Barr virus. And because David had zero functioning T cells to keep that dormant virus in check, the virus woke up, raged out of control, and triggered a fatal lymphoma. He passed away in 1984.
It was a huge blow to the medical community.
So what does this all mean for us today? Because David's tragedy completely changed modern pediatrics. It's the exact reason why all 50 U.S. states now screen every single newborn for SCID using a heel prick test. They look for something called TRX. How does that test actually work?
So think of TRX like sawdust left on a factory floor.
Okay, sawdust.
When the body successfully manufactures a mature T cell in the thymus gland, the genetic cutting and pasting process leaves behind these tiny circular loops of DNA. Those are the T ranks.
Oh, I see.
If doctors prick a baby's heel and they don't find any of that DNA sawdust in the blood, they know the T cell factory never even opened for business.
Wow.
Because of David, a disease that was an absolute fatal mystery in the 70s is now a treatable finding before a baby even gets their first infection.
That's an incredible legacy.
But getting to that point of successful treatment wasn't a straight line. Robert Good performed the first successful bone marrow transplant for a SCID patient back in 1968, proving you could theoretically replace a broken immune system.
Right.
But when researchers moved into the era of gene therapy in the early 2000s, attempting to fix the patient's own cells rather than using a donor, they encountered a massive, heartbreaking hurdle.
You're talking about the French gene therapy trial.
I am. Researchers in France extracted bone marrow from children with X-linked SCID. They used a retroviral vector, essentially a hollowed-out virus acting as a delivery truck, to insert a healthy corrected gene into those stem cells and then gave them back to the patients.
Okay.
Initially, it was a medical miracle. The children developed functioning immune systems and left their isolation bubbles.
That sounds like a massive success.
It did, but a few years later, several of them developed leukemia.
Oh, wow. Because of the mechanism of how that delivery truck works, right? Like retroviruses don't just drop off the gene, they physically weave it into the patient's DNA.
That is the core issue, yes. It's a process called insertional mutagenesis. The retroviral vector accidentally inserted the healthy gene right next to a naturally occurring oncogene called LMO2.
And oncogenes cause cancer.
Right, they regulate cell division. So the delivery truck essentially acted like a stuck gas pedal, forcing that LMO2 gene to turn on and stay on. And that triggered uncontrolled white blood cell growth, which is cancer.
That's devastating.
It was a huge setback, but it completely forced the scientific field to redesign how we deliver gene therapies, leading to the much safer vectors that we use today.
Here's where it gets really interesting, though. We've spent this time talking about genetic primary errors, the inborn conditions, but they are incredibly rare. Secondary immunodeficiency, meaning acquired, where your shield was built correctly but gets dismantled later in life, that affects millions of people.
Millions, yes.
And there is a massive misconception here. When people hear acquired immunodeficiency, they immediately think of HIV. But HIV isn't the #1 cause globally, is it?
Not even close. While HIV is the paradigm we all study, the single largest cause of secondary immunodeficiency worldwide is actually malnutrition.
Malnutrition.
Yeah. Building and fueling white blood cells requires an immense amount of metabolic energy, protein, and micronutrients like zinc. If a person is starving, the bone marrow simply shuts down production. The body prioritizes keeping the heart and brain running over manufacturing SWAT teams.
That makes total sense physiologically. But HIV fundamentally changed our modern understanding of how a virus can specifically target and dismantle that architecture we talked about.
It really did. The clinical history of HIV is a masterclass in how immune depletion dictates disease. In June 1981, the CDC published a report about 5 young gay men in Los Angeles who had developed pneumocystis pneumonia.
Which is an opportunistic infection. To use our earlier analogy, it's a weak pathogen that a normal bouncer would just swat away effortlessly.
Exactly. The presence of that specific pneumonia was the clinical signature that the immune shield was entirely gone. We eventually learned that HIV specifically targets CD4 positive T helper cells.
And what did those do?
These are essentially the commanders that coordinate the entire SWAT team and the aerial support. The virus uses those commanders as factories to replicate, completely destroying them in the process.
Wow.
And clinicians track this destruction purely by the numbers. A normal CD4 count is roughly 500 to 1,500. AIDS is officially diagnosed when that count drops below 200, or when an opportunistic infection takes hold.
Now, navigating the history of HIV also means confronting how society handles that science. Looking purely at the historical record provided in our sources, one of the most consequential events was the South African AIDS denialism in the early 2000s.
Yes.
Under President Thabo Mbeki, the government was heavily influenced by a fringe theory promoted by a researcher named Peter Duesberg, who claimed that HIV does not cause AIDS. And based on this theory, the South African government restricted access to proven life-saving antiretroviral drugs.
Right.
A Harvard School of Public Health analysis later estimated that this specific policy of substituting ideology for settled science resulted in over 330,000 preventable deaths. It is a staggering, objective, historical fact about the devastating cost of ignoring how a virus works.
It really is. And, the intersection of HIV and genetics continues to push boundaries today. There's a naturally occurring genetic mutation called CCR5 delta 32.
CCR5 delta 32, what does that do?
Well, HIV relies on a specific receptor, the CCR5 protein, to grab onto a T cell and gain entry. If you have the delta 32 mutation, that receptor is warped. You are essentially missing the doorknob the virus uses to get in, rendering you highly resistant to HIV.
That's wild.
Yeah, and two famous cases known as the Berlin and London patients were actually cured of HIV after receiving bone marrow transplants from donors who naturally had this exact mutation.
Which sounds like an incredible avenue for a cure. But it sparked one of the most intense ethical and scientific firestorms of our lifetime. In 2018, a Chinese scientist used CRISPR gene editing technology to artificially engineer this exact mutation into twin embryos.
He did, and he was condemned by the global scientific community and ultimately imprisoned. Beyond the ethical violation of experimenting on human embryos, the science itself was just reckless.
Because of the unknowns.
Exactly. Modifying the human germline when we don't fully understand the downstream, off-target effects is incredibly dangerous. Tinkering with the shield has consequences. We know, for instance, that while removing that CCR5 doorknob blocks HIV, it actually makes the immune system much more susceptible to other severe viral infections, like West Nile virus.
You solve one problem by opening the door to another.
Exactly.
And that brings us to why all of this matters for you, the listener, right now, today. Because immunodeficiency isn't just about rare genetics or historical viruses. It is woven into everyday modern medicine.
It's an everyday clinical reality. We have to consider iatrogenic or medically induced immunodeficiency. Millions of people are walking around right now on powerful immunosuppressive drugs.
Right.
If you've had a kidney transplant, or if you have an autoimmune condition like Crohn's disease or rheumatoid arthritis where your immune system is attacking your joints or gut, you are deliberately taking medications to lower your shield.
And we saw exactly how crucial this population is during the COVID-19 pandemic. Immunocompromised patients tragically acted as live incubators. Because their lowered shields couldn't clear the virus quickly, the virus was able to linger in their bodies for months, constantly mutating and test-driving new escape mechanisms.
Yeah.
Researchers believe this was a major pathway for the emergence of new, highly contagious variants that affected the entire globe.
And even if you never take an immunosuppressant, if you are lucky enough to grow old, you will experience a weakened shield. There is a biological process called immunosenescence.
Immunosenescence?
Yeah, it is the gradual, universal decline of immune function with age. The thymus gland shrinks, T-cell production drops, and the existing cells just get exhausted.
The shield just naturally gets heavy and starts to lower over time,
Yep.
but fixing a lowered shield isn't always as simple as just turning it back on. Let's look at the concept of IRIS. What exactly is that?
So IRIS stands for Immune Reconstitution Inflammatory Syndrome. It's a bizarre, paradoxical danger that highlights how carefully the immune system has to be balanced. Imagine you have a severely immunodeficient patient, perhaps someone with advanced HIV. Because their shield is down, their body is secretly harboring multiple latent infections, fungi or viruses, that are slowly replicating, completely undetected.
Because the alarms aren't sounding.
Right. But if you suddenly fix their immune system by starting them on powerful antiretrovirals, their newly awakened T cells suddenly look around and see all the threats they missed.
It's like turning the lights on in a filthy room, and the cleaning crew just loses their minds. They start furiously tearing the house apart to clean it.
That is a very apt way to visualize it. The awakened immune system mounts an explosive, massive inflammatory response to clear the infections. That hyperinflammation can cause severe tissue damage, brain swelling, and can actually be more immediately dangerous to the patient than the original slow-growing infections themselves.
Unbelievable. So, to wrap this all up for you, we've covered some incredible complex ground today. The biggest takeaways: immunodeficiency is fundamentally about function over numbers. Having a normal cell count doesn't mean your bouncers actually have the chemical weapons to do their job.
Absolutely.
We learned that immune deficiency and autoimmunity share the exact same genetic roots. A missing brake pedal can cause the system to fail against a virus while simultaneously destroying your own body. And we've seen that history's biggest lessons, from early gene therapy causing leukemia to the dangers of IRIS, prove that interacting with our immune system requires immense humility.
The underlying science is incredibly powerful, but the sheer complexity of our microscopic defenses demands profound respect.
Which leaves me with one final thought for you to mull over. If our immune systems naturally decline as we age, and medical science is simultaneously getting incredibly good at keeping millions of people alive using immunosuppressive drugs for transplants and autoimmune diseases, are we slowly engineering a future where the baseline of human immunity is fundamentally different? And if a massive portion of the population is walking around with a lowered shield, how does that force us to rethink the way we design our cities, our public spaces, and how we live together? Next time you touch a doorknob, just remember, The shield is invisible, but it shapes absolutely everything.